Hello teacher, I am Đặng Quốc Bảo. Today, our group would like to present the topic Design and Simulation of an 8-bit parity generator and checker with comparison to Hamming code, which was implemented using on 90 nanometer CMOS technology under the supervision of Dr. Phạm Văn Khoa. Our group consists of the following members: Nguyễn Trịnh Khánh Linh, Đặng Quốc Bảo, Võ Tấn Phát, Trần Gia Phú, and here is our task distribution table. About the main content, the report is divided into 5 chapters. Chapter 1, Overview. Chapter 2, Technology Platform and Logic Gate Use. Chapter 3, Parity Code, the seamless error detecting code. Chapter 4, Error detecting and error correcting using Hamming code. And the last is Chapter 5, Conclusion and Future Development. Now, I would like to present Chapter 1, Overview. In modern digital systems, data transmission and storage require high accuracy and reliability, but noise, signal loss, or hardware faults can corrupt data. To address this, error detection and correction codes are used. The parity code is the simplest, adding a single check bit to detect error but cannot correct them. The Hamming code improves on this by detecting and correcting single bit error and is widely used in memory and communication system. Our project design and simulate an 8-bit parity generator and checker, then compare it with the Hamming code to illustrate the difference between detection and correction. Using cadence potential with TSMC 90 nanometer technology, we analyze delay, power, accuracy, and compare complexity with error handling capability. Simulation confirmed that Hamming code extends parity code to provide higher reliability in digital circuits. And in Chapter 2 presents the technology platform and basic logic gates used in our parity and Hamming code circuits. We implement the circuits using TSMC's 90 nanometer CMOS process and analyze gates such as NOT, N for input N, and for to 16 decoder, and XOR in terms of delay, power, and temperature. The 90 nano process balance cost, performance, and complexity, support multiple voltage and response options, and is widely used in research and industry. At this note, careful management of fan-in, fan-out, and parasitic is required, as the dynamic power dominates while leakage becomes noticeable, affecting scalability for larger data widths. And the next part is logic gate used for parity and Hamming code. The first is NOT gate. This is the schematic, symbol, and truth table of the NOT gate. The structure consists of one PMOS and one NMOS in the pull-up network and pull-down network, connect in series between VDD and GND. When the input A equal to 0, the PMOS conduct and the NMOS is off, so the output Y equal to 1. And when A equal to 1, the PMOS is off and the NMOS conduct, so the output Y equal to 0. So the output is on-way inversion of the input. The BUN pull the output voltage up to VDD, while the BGN pull it down to GND. And here is about the optimal quick overlap ratio. Based on the conduction characteristic of transistor, we know that an NMOS has twice the price range of a PMOS. Therefore, to balance the rise and fall speed, or to TBLH approximately equal to TBHL, we choose the ratio here. This ratio helps optimize the propagation delay of the NOT gate. And this is the schematic and symbol in cadence. And here is the table of simulation parameter. From the waveform, we observe that at on time, the output y is the inverse of the input 8, and the propagation delay is the time by which the output signal changes slightly later than the input signal, and it is calculated using this formula. During this measurement, we test at two different supply voltages, 1 and 1.2 volt. At 1 volt, the software measures at TPD approximately 6.4 picosecond. This means that from the moment the input changes, it takes approximately 6.4 picoseconds for the output to reach its new stable state. And when VDD increases to 1.2 volt, the transistor right current increase makes the charging and discharging of a capacitance is faster, so the propagation delay decreases to about 5.56 picoseconds. This indicates that the higher VDD allows the circuit to switch faster, reduce the time required to charge and discharge the circuit's capacitance. About the power consumption analysis, the total power consumption consists of two main components, B total equal to B dynamic plus B static, where B dynamic is calculated by this formula, and this is the dominant component of total power. From the simulation result, understand the condition at 27 Celsius degree, VDD equal to 1 volt and frequency equal to 50 MHz. The average power is here. And when we change the condition, increasing temperature to 80 Celsius degree, both dynamic and static power increase due to change in carrier mobility and higher liquid current. So total power rise and energy efficiency decrease at high temperature. When we increase frequency to 100 and 150 MHz, dynamic power increase almost linearly with the frequency, but static power remains nearly constant. And when increasing VDD, dynamic power increase proportional to VDD square. Static power increase slightly due to higher liquid current, so the total power rises sharply. And next, we have the two input CMOS AND gate. In figure 3.2.1 and 3.2.2, we can see the schematic and symbol of the two input CMOS AND gate. It is constructed by combining a NAND gate and a NOT gate. NAND talk consists of two PMOS in parallel forming the pull-up network and two NMOS in series forming the pull-down network. When pole A and B are on, pole NMOS conduct and pole PMOS are off, so the intermediate node is pulled down. But for any other input combination, at least one PMOS conduct connecting the intermediate to VDD, and then the inverter will yield the final output Y. Y equal to 1 only when pole A and B are 1. This matches the truth table of the AND gate shown in table 3.2.1. And here are the width over length ratio of transistor with the simulation parameters. This configuration ensures a balanced write and hold time, optimizing the propagation delay. The waveform perfectly matches the truth table. The output Y goes high only when both inputs are 1, and for all other input combinations, Y remains 0. The propagation delay of AND gate is shown in the table below. We can observe that when VDD increases to 1.2 volt, both TPLH and TPHL decrease, so the average propagation delay TPD dropping. And the simulation results for AND gate power consumption are summarized as follows. Increasing VDD, power increase proportional to the square of voltage. Increasing frequency, power increase almost linearly, and increasing temperature, static power rise due to liquid current. And next, we have the 4-input AND gate. Two figures show the schematic and symbol of the 4-input AND gate, which is constructed by cascading three 2-input AND gates. At first stage, combine A and B to produce the intermediate output Y1, and second stage, combine C and D to produce Y2. So final stage generate the final output Y. When A, B, C, and D are 1, the intermediate output are high, and the final output Y is also logic 1. And here are simulation parameters. Based on the truth table, the output waveform can be described as follows. When any input A, B, C, or D equal to 0, the output Y remains 0. And it only rises logic 1 when all 4 inputs are simultaneously at logic 1. And here are the propagation delay and power consumption. The 4-input AND gate has a larger delay than the 2-input AND gate due to the additional logic stage. And the next, we have the 4 to 16 CMOS decoder. This figure shows the schematic of the 4 to 16 decoder, which is constructed from 4 NOT gates and 16 4-input AND gates. The decoder receives 4 binary inputs and produces 16 outputs with only one output high for each input combination. The NOT gate generates the complement signal from the corresponding inputs, and the 4-input AND gates combine the original and complement signal to produce each unique output. For example, D0 equal to 1, D0 equal to S3 bar, point S2 bar, point S1 bar, point S0 bar, and D15 equal to S3, point S2, point S1, point S0. When a specific 4-bit combination is applied, only the corresponding AND gate has on input as logic 1, producing a single high output, while all other output remain low. And about simulation parameter and output waveform. The waveform shows a one-hot pattern with a logic 1 moving sequentially among outputs as the input combination change. And the average TPD per output is significantly larger than that of a 4-input AND gate due to the multiple cascade and stage. When we increasing VDD to 1.2 volt, reducing the delay, allowing the circuit to switch faster, and the total power of the decoder is relatively high because the larger number of transistors and many logic states. And when VDD increase from 1 to 1.2 volt, total power rise, confirming that VDD has the strongest impact on energy consumption. And finally, we have the 2-input XOR gate. In CMOS circuit design, XOR gate is one of the most challenging gates to design because it must be fast, compact, low power, and have two rail-to-rail output. This figure shows several common XOR implementation. Figure 3.5.1a and b are basic logic gate. It's easy to understand and draw, but has high delay, many transistors, and high power consumption, so it's not optimal. Figure C and D are standard complementary CMOS XOR. Use complementary NMOS and PMOS network. Output is rail-to-rail and stable. This form using a transistor for PMOS on top and for NMOS at bottom. Uh, in this figure D is the improved CMOS XOR because it optimized by removing two contacts compared to figure C. So smaller area, fast speed, and widely used in commercial standard cell libraries. And the rest are some other two input XOR configuration for reference. So for this project, I will show the improved CMOS XOR in figure D because rail-to-rail output ensure rubber logic level 0 and 1 meeting CMOS standard. And it's widely used in CMOS technology such as TSMC or Xilinx. So it balancing speed and reliability. And the third is it's easy to simulate and stable across on VDD level, suitable for Parity and Hamilton application. And because this is the version that we had learned. The two input XOR gate consist of 4 PMOS in the pull-up network and 4 NMOS in the pull-down network. In pull-up network, two transistors A and B in parallel connect in series with two transistors A bar and B bar in parallel. When A different to B, there is a complete path to VDD producing Y equal to 1. And in pull-down network, two transistors A bar and B bar in series and it in parallel with two transistors A and B in series. So when A equal to B, 0, or 1, there is a path to GND producing Y equal to 0. Um, and here is the stable state and transistor parameter used to optimize delay. In this session, a short comparison will be made between two XOR circuit types. So in figure C and D, we comparison about delay and power consumption under identical simulation condition to determine the more optimal design for future implementation. The schematic of XOR gate C and D show that uh, type D is optimal compared to type C by removing two contacts. So it reducing area and delay. And the waveform show that the output goes high only when the two inputs are different. If the inputs are the same, the output is 0. So this is suitable for parity and Hamming encoding. About the propagation delay and power consumption, under standard condition, VDD equal to 1, temperature equal to 27 Celsius degree, and frequency is 50 MHz. Type D show lower delay and power compared to Type C. Therefore, Type D is more optimal in terms of both speed and power, making it the preferred choice for parity and Hamming designs. And here are some simulation results of delay and power for Type D under different operating conditions.
First of all, I would like to send my greeting to the subject teacher. My name is Ivan. My student ID is 223 1 0 2 and 7. Today I'm going to present about parity cost. It considered seamless form of errors detection used in a digital communication systems. In the presentation, I will first explain the theoretical aspect, including the definition, mechanisms, operating reasonable, and parity coders. After that, my partner in my team four we discussed the general block diagram of parity system and parity decoder checker. To begin with, let's start by understanding what is the parity because actually is in a digital system that can easily be corrupted during transmission or storage due to the factors such as electrical noise or hardware failures. To detect these possible errors, we use a simple technique known as parity checker. Parity is an additional binary bit added to the data work to ensure that total number of ones in the sequence second flow are free. Define proves either even or odd. You can see here a parity bit and extra bit that's added to the message bit or data work bit on the sender side. Data work bit along with the parity bit are called the coarse work. And in parity bit we have consist of the old parity and even parity. About old parity, the total number of one including parity bit um, the rest is old. Uh, the total number of one in a given binary string or data bits are even this one is expanded to make the total count of one as of L0 is expanded. Next, we go to even parity. Even parity, the total number of one including the parity bits is even. So we can see that the total number of ones in the given data this should be even, or if the total number of one in the database is odd, then a single one piece will be expanded to make the total number of the ones even. L0 is be expanded if the total number of one is already even. We can say the actual picture explain about this the event parity generator and yeah. So now that's we know what parity is. Let's see how it actually works in practice. At the transistor side, the system count number ones in the data work depending on whether we are using even or odd parity. The appropriate parity bit is calculated and appended to the end of the frame before it is sent. You can see that example we have original 8-bit data and we have five ones in this original 8-bit data and we know it's old. It's a parity type even. The P parity bits calculators give you ones and transmitted 9-bit frame you have 1 1 1 0 0 0 0 1 and as 1. Okay. Next we go to we talk about at the receiver. At the receiver side, the same process occurs again. The receiver check the numbers of one it received frame including parity bits and compares it to expected parity rules. If the total number of ones satisfies the rules, the data is considered valid. Yes, if not, it indicates that error has occurred during the transmission. However, this method has a limitation. It can only detect single bit errors. It's 2 or more bits, it's like 3 bits or 5 bits. It changes simultaneously. The total parity might remain unchanged, making the error indetectable.
Now, let's talk about the operating principle and calculation formula of even parity. In even parity, the parity bit is generated using the XR operation on all the data bits. The idea is to make sure that the total number of ones in the whole sequence, including the parity bit, is even. For 8-bit data, the formula is shown here. B equal D7 XOR, D6 XOR, and so on until D0, where D7 to D0 are the 8 data bits, and B is the parity bit. At the receiver side, the same XOR operation is applied to check for errors. If the final result is 0, that means no error is detected. If it's 1, that means there has been a transmission error. Here we can see a simple example. Let's take the data 11000001. There are 3 ones, which is an odd number, so we add the parity bit of 1 to make the total count even. The transmitted frame become 1100000011. Now, if an error occurs, say 1 bit flip during transmission, the number of ones in the received frame will no longer be even. The difference allows the system to detect that an error has occurred. Now let's move on to the general block diagram of the parity system. As shown here, the process starts with the data input, which provides the original binary bits to be transmitted. This can come from a processor, memory, or a sensor before any error checking is done. Next, the data goes to the parity encoder, also called the generator. This block adds the parity bit, either even or odd, to help detect single-bit error during transmission. After that, the signal passes through the transmission channel, which carry the data from the sender to the receiver. This can be a wire or wireless connection, but it's also where the noise or interference may introduce errors. At the receiving end, the parity decoder or checker verifies the parity of the received data. It recalculates the parity and compares it with the received parity bit to detect any errors. Finally, we have the output result block. If the data is correct, it's accepted. Otherwise, the system indicates an error or trigger a retransmission. In short, this diagram shows the overall flow of how parity bits are generated, transmitted, and checked to ensure reliable data communication.
Now, let's take a closer at the component responsible of generating the parity bit, the parity encoder. We can say parity generators. The parity encoder or generators is located at the transmitter side. It receives a set of data bits come to the parity using its OR gates and expanded the resulting parity bits to the data frame. Its operating as follows. If the number of 1 in a data is even, the parity bit is set to 0. If number of 1 is odd, the parity bit is set to 1. This encoder can be implemented using the series tree structure of its OR gates because its OR gate output 1 when the number of high input is odd. It naturally fits the logic required parity generation. Now, let's take a closer look at the component responsible of generating parity bits, parity encoders. We can count the parity bit encoders is a parity generator, and the parity encoders is located at the transmitter side. It receives a set of data bits, compute the parity using its OR gate, and expand the receiving parity to the data frame. You can see the parity generator in the main function. A parity generator circuit is combinational logic circuits that is used at the transmitting end. Its primary function is to calculate and add the parity bit to the data stream based on the chosen parity scheme, even or odd. And input is n-bit data, output is 1-bit parity. Let's talk about the characteristic example. even parity encoder, the parity bit is chosen so that the total number of 1 bits encoding the parity bits is even. If the data already constant an even number of 1 bits, parity equals 0. If the data constant an odd number of 1 bits, the parity equals 1. Closer with the structure of parity encoder implemented using XOR gates connected in a series or in a tree structure, since XOR equals 1 when the number of high 1. Input is out. Now what now to clearly with this theoretical about the parity encoder, we can use simulate to describe it. Okay, next we talk about the specification and simulation. You can see in this simulation, this is a 8-bit generator, parity generator, and with formula D equal D7, XOR D6, XOR D5, XOR D4, XOR D3, XOR D2, XOR D1, and XOR D0. In this part of the experiment, I will represent the simulation result of the 8-bit parity encoders or generator element in a cadence virtual. The goal of the simulation is to verify the circuit logic, behavior, timing delay, and power consumption under different operating conditions, such as the supply behavior, timing delay, and power consumption under different operating conditions, such as the supply, voltage, frequency, and temperatures. Let's begin by explaining the signal line and input-output port in the parity encoder circuit. We know in this circuit we have all the 8 data bits labeled as D0 to D7, represent the original binary information to be transmitted. Its input can take either logic 0 or 1. We can see binary 8-bit encoder, and this is the parity 8-bit decoder packet. The outputs of the circuit is the parity bit V. You can see this. On B, this output generates by or is a combination of 8 input bits for an even parity encoder. The output P is chosen as total number of logic 1 in the entire frame, including P is even. In other words, if the number of 1 among to 0 to D7 is even, the output P equals 0. If the number is odd, the output P equals 1. During simulation, all input lines were driven by a periodic pulse through specific timing parameter observe the logical switching behavior. Before we analyzing the waveform of 8-bit parity decoders, let's look at the simulation setup. We can see we have a parameter value delay of VDGs have 1 volt, okay, and parameter D0 to D7 we have we can see the value of D0 to D7 parameter are different, but the delay not change much. To be clear, we will dive deeper into the wave. Now let's move the simulation waveform of the parity encoder. In this figure, 5.4 parity encoder waveform, we can observe that input bits D0 to D7 switch periodically between the logic highs and logic low. The output bit respond according the after small propagation delay. Let's consider one time interval as an example from the T from the T0 to the D7. During this period, several input change their logic state. The XOR operation inside the encoder will compute the total parity in real time. As a result, we tell the total number 1 as small D0 to D7 become also the output immediately switching to 1. And when the total number of 1 is even again, the output returns to logic 0. This verifies that circuits correctly implement even parity generation. Okay. Next, we will talk about the propagation delay analysis. The propagation delay is the time difference between as the input transition of the corresponding output response. According to the live result form shown in table 5.2, we can see VDD trend 1 volt to 1.2 volt. TPLH with picosecond had chance and TPD with picosecond had chance. All of them are changed. From the table, we can observe that when the VDD increase from the 1 volt to 1.2 volt, the propagation delay tends to decrease. We can see when VDD 1 volt, TPD 132.02. But when VDD is 1.2, the TPD change to 123.55. Why? This is because the higher supply voltage allows the transistor to switch faster, thus reducing delay and improving circuit speed. About the power consumption analysis. Okay, let's analyze the power consumption result from table 5.3. We can see as VDD 1 volt, we can see 50 megahertz and temperature equals 27 degrees Celsius. At the dynamic powers 2680, the static 154.6 nanowatt, and the totals is 2834.6. Now let's look at the variation when the temperature decrease to a minus 20 degrees Celsius. The pole dynamic and static power decrease. You see that? In places, the total power is 2551.29. This happens because the lower temperatures reduce the transistor leakage and switching the losses. So next, when we increase the temperatures to 80 degrees Celsius, we can see the bit dynamic, the power, bit dynamic changed to 2967 nanowatt, and bistatic changed to 276. We can see when we increase the temperature, uh, this to high galactic current and reduce the resistor efficient at elevated temperatures. And when it change to 1 volt to 1.2 volt, the total number rise to 4666.3 nanowatt. Sync power is proportional of V VH2 in the CMOS circuit. Summary, we can know the lower temperatures imply a lower power. Higher temperatures implies the higher power. Higher VDD implies a higher power consumption.
Moving to the parity checker, which is located on the receiver side, and its job is to verify whether the received data is valid or not. The inputs here are 8 data bits plus 1 parity bit, and the output is a single error bit. It can be either 0 or 1. Now for even parity, the operating principle is quite simple. If the total number of ones including the parity bit is even, that means the data is valid, so the output will be 0. But if the total number of ones is odd, it means an error has occurred during transmission, and the output will be 1. In practice, the checking circuit uses XOR gate to count the number of ones and determine whether the total is even or odd. That's how it detects any transmission errors. Moving to figure 6.1, the parity decoder schematic. We can see the input signals include D0 to D7 and one parity bit, which is generated from the parity encoder. The output is the error bit. When the error bit equals 0, it means the data is correct, no errors. But when the error bit equals 1, it indicates an error has occurred. Now in table 6.1, we can see the simulated signal parameter with VDD has 1 volt, TD0 5 nanosecond with a delay of 0 nanosecond, TD1 10 nanosecond, TD2 20 nanosecond, TD3 40 nanosecond, TD4 80 nanosecond, TD5 160 nanosecond, TD6 40 nanosecond, and TD7 20 nanosecond. All of them has a delay of 0 nanosecond. In figure 6.2, we can see the parity encoder symbol. And in figure 6.3, we can see the parity decoder waveform. In the first time period, all signal from D0 to D7 and the parity bit B are at logic 1. That means we have 9 1 bits in total, which is an odd number, so the error output go high. Error equal 1, showing that an error is detected. In the second period, D0 changes to 0, leaving us with 8 ones. 8 is an even number, so the error bits become 1, meaning the data is valid. In the third period, all bits are 1 except D1 and B, which are 0. That gives us 7 ones and 2 0. 7 is odd, so again the error bit is 1, showing a transmission error. In the first period, D0, D1, and B are all 0, which leaves 6 1 in total. 6 is even, so the error bits return to 0, indicating valid data. And finally, in the fifth period, D2 and D7 are 0, leaving 7 1s. 7 is odd, so the error bits go back to 1, meaning there's a detected error again. Moving to figure 6.4, which is the parity decoder operation delay at 1 volt. And at figure 6.1, the parity decoder operation delay at 1.2 volt. Now moving to table 6.2, the parity decoder delay at different supply voltages. We can see that at VDD 1.2 volts, we have TBLH at 30.27 picosecond, at TBHL at 164.78 picosecond, TBD at 97.53 picosecond. With VDD at 1 volt, we have TBLH at 184.41 picosecond, TBHL at 33.53 picosecond, TBD at 110.97 picosecond. Now moving to table 6.3, we can see the parity decoder power variation under different conditions. At 1 volt, 50 megahertz, 27 degrees Celsius, we have the dynamic power at 4203 nanowatts and the static power at 230.1 nanowatts, which give us the total power at 4433.1 nanowatts. As we can see, when the temperature decreases, the total power also decreases. But when the temperature rises to 80 degrees Celsius, the total power also goes up. Also, moving on to the frequency, we can see at 100 megahertz, the total power is 5410.1 nanowatts. But at 115 megahertz, the total power goes down to 1503.1 nanowatts. But when we change the voltage to 1.2, keeping the frequency temperature the same, we can see the dynamic power and static power increase alongside, giving us a total power of 7,869.8 nanowatts.
And next, I will present the parity encoder and decoder structure for error detection. In this session, we simulate the combined operation of both encoder and decoder, forming a complete parity system. The figures show the combined encoder and decoder schematic. In parity encoder, generate a parity bit from a bit data. We use even parity. So if the total number of 1 in the A data bit is off, the parity bit is set to 1 to make the total number of 1 in 9 bits even. So, and if the total number of 1 in the A bit data is even, the parity bit is equal to 0. And in the parity decoder block, each function is receive a 9 bits, uh, mm, including a data bit and 1 bit parity to check for errors. And to simulate 1 bit error, a noise bit is added. The zero is altered during transmission through the decoder. Initially, the zero equal to 1 pulse normally, but when transmit through the decoder, the zero noise equal to 1 bit, while the other bits, D1 to D7 and the parity bits remain correct. So this creates a single bit error scenario to observe the detection capability of the parity system. And this setting allow on correct and error case to be observed in the output wafer. So in this wafer, at the first time interval, uh, all input bits equal to 1, so parity bit equal to 0. Um, Passing through the decoder, the 0 noise equal to 1 matches the actual value, so error output equal to 0, indicating no error. But at this time interval, um, input bits equal to 0, 1, 1, 0, 1, 1, 1, 1. So the parity bit equal to 0. But with the 0 noise equal to 1, XORing on 9 bits result in an odd total. So error output equal to 1. It indicating detect a 1 bit error. At other time interval, similarly demonstrate the fully parity behavior, showing how a single bit error is detected during transmission or storage. And here is the output or error bit delay time, meaning the time from applying the A bit data to the error flag activation. When we increase VDD from 1 to 1.2 volt, slightly increase delay, but the parity encoder and decoder have acceptable delay, so ensuring immediate error detection after data input. And here is the power consumption of parity encoder and decoder. Um, Overall, the delay and power are within acceptable limits, making this design suitable for error checking in VLSI circuits.
Now, now we know about parity bits theory. Also, we need to discuss the design and operation of the parity code system. Let's analyze its advantages and limitations. This help us understand why it remains widely used despite being a very basic error detection technique. First, the advantage is simplicity of design. The particles have an extreme simple structure which makes it's easy to implement using basic logic. And guys, using as XOR, we know parity bits are created with XOR gate. By using XOR gates, this simplicity reduces circuit complexity, cost, and design time. Second, the single bit error detection. It effectively detects single bit errors that may occur during data transmission or sustain, ensuring a basic level of reliability for digital system. Number three, the wide applicability. The parity checking is common integrated into the fundamental communication protocol such as OAOT and OAOT. This is example about OAOT, RS true and true, and in order memory module MMO, where simplicity and speed up prioritizes. However, the technique also comes with several limitations that restrict its use in a modern high reliability system. Limitation limit error detection capability. The parity method fails to detect error when an even number of bits, for example, 2, 4, or more, are covered because the total of parity count remains unchanged. As a result, the multi-bit error can go unnoticed. Number 2, no error localization. Even when a single bit error is detected, the system cannot determine which a specific bit is incorrect. It only indicates that an error occurs nowhere exists. And number 3, no error correction. The parity code can detect error but cannot correct them. This means that Retransmission or higher level correction methods are required to ensure data integrity. To summarize this session, the parity codes in efficient or simple system where reliability requirements are moderate, but it's not sufficient for application demanding high fault tolerance or automatic error correction. This limitation motivates the development of more advanced coding methods such as harming costs and set detect single error correction, double error detection, which build upon the same is all the foundation to achieve more robust error control. About the harming cost, my next we talk about this. Okay, about conclusion about parity IP. To conclude, the parity code represents the most fundamental form of error detection in digital communication and information processing system. Although its structure is simple, its underlying is always logic serves as a conceptual um, response for many modern error checking algorithms. By ensuring that the total number of one data frame follow a consistent parity rules, the system can quickly verify uh, the correctness of the transmitted of the storage data. Even though the parity encoder cannot locate or correct error, it performs an essential role at the first level defense in data integrity. This minimal hardware requirement and fast operation is radical choice for small-scale or resource-limited system. In summary, we can say that the parity cost is not just the legacy methods, the foundation upon which modern error detection and correction techniques are built. And as we move forward, the next part of the presentation, we will explore the hummingbird.
We're gonna go with the next part is having cost. With previous part, you already know that the Y transmission, the bit have ability to flip from 0 to 1 or 1 to 0. And the having card is just only detect the Android, but it's don't know where actually the bit Android is and physics. And this is a reason that the Hamming card was born. And the Hamming cards were developed as an extension of the parity concept. The Hamming card will not only detect but also correct single bit Android, so make it uh, widely used in memory system, storage device, and communication link. So how the Hamming card work? Um, it doesn't like the parity. It doesn't like the parity card that just use one bit check. The Hamming card use multiple check bits insert into specific position. And here I show you a table that example. I want to send. I want to send a data bit, and you can see that at the bit position 1, 2, and 4, and 8, we have the parity bit 1, parity bit 2, parity bit 3, and parity bit 4. It can be based on the formula that 2 to power of n minus 1 that assemble with the parity bit 1 is P1 is will be 2 uh power 2 to power 1 minus 1 is to power of 0, so it must be position 1. So each parity bit not only check a small group of database but also overlap parity code with other groups, forming an interleaved structure. So to show you more, understand more about it, I gonna go with the next example. So I have three kind of circle here. I will call this circle A, B, and C, and we can see the data bit inside the circle that is overlap each other, and also in the circle we also see the data bit is uh, is also known as a small group that the data bit will check. Uh, at the picture B, you can see that we have three number one in the circle A, so the parity bit in here will be one. And with the circle B, we have two number one, so the parity bit will be zero. And we do the same with the third circle is circle C, it will be 0, 2. And with the number C, we can see that now the bit 1 inside the circle A and circle C flip up from 1 to 0. And at the number C, the parity bit inside the circle A is not one anymore. It must be zero for sure. And with the circle C, it must be one for sure. So from that, go to the picture D, we can detect the error that the bit zero in here. So So we know that we must use multiple check bits, but how many check bits is required for data sequence? Sequence of m bit, with m is the original data bit. It will based on the formula that 2 to power of k and minus 1 gonna greater or equal with the m plus with k. I get an example. I have AB data and the k will be 4 because the a to power 4 will be 16 and minus 1 will be 15. It is greater than the m plus k that will be 12. So k is okay. And the next one, we know that the parity pip will check a small group. So what which position that the parity bit will check is very simple, that based on the rule that skip the first n minus 1 bit and take the next n bit and skip another n bit, take another n bit, and so on, continue to pattern until the end of the sequence. The samples in here, we have that we pick one, um, n will be 1, 1 minus 1 will be 0, so we do not skip any bit. And we start with 1 bit in number 1, skip bit 2 and take bit 3, and skip bit 4 and take bit 5. We do the same at the end of the consequence of the sequence. And we do the same with another parity bit 2. So the convert data bit will be D0, D1, D3, D4, and D6. So the comparison is performed bit by bit using the XOR operation between the old and new parity bits. The result of this comparison is called the syndrome. Each bit of the syndrome has the following meaning. One, if the two corresponding bits are identical, it means they have no error, and one, if the two corresponding bits differ, this means the error detected at that position. So for you to understand more, I also have an example that with the ball we have a bit input data is 00111001. For calculate the parity, we calculate the parity bit. We know that P1 will be equal 1, P2 will be equal 1, P4 is will be equal 1, and PA is will be 0. And while transmission, the D2 will be have the error that it changed from 0 to 1. And now, so on, we're gonna have the data after transmit is 0011110001. So now the new parity bit will be P1 equal 1, P2 equals 0, P4 equals 0, and P8 it will be 0 too. So the synchrone happen at the next step in here that we XOR the old parity bit with the new parity bit. With old parity bit is the parity P4 the data transmission. Then the new parity bit is the data after transmission. So with before transmission, the parity bit will be 0111, and it will be XOR with the new parity is 0001. So we have the so it will be 0110, and with the bit number 6, it will be D2, like I said in here. So so now you are already understand about the Hamming curve. So what is the structure of Hamming curve or error correction? We have two sides, is the sender and receiver. With the sender, it will be the input will be k bit. Is here I will be assemble. It will be 8 bit, and the data will be go to the Hamming generator that it will take from it will be created 4 parity bit from a data bit, and assume this parity bit with data bit to create the n bit, and then it will send to the unreliable transmission. Of course, in the unreliable transmission, it has ability to the bit that trend from 0 to 1 or 1 to 0. And at the receiver, I say the decoder, I say Hamming decoder. It will be go to the Hamming checker, parity checker, that in here it will take the A data bit after transmission and to create the for new parity data, for new parity bit, and then they will XOR the new parity bit with the old parity bit together to know where the error happened, and then correct it and go to the output. So this is what we're gonna simulate in the cadence using GPK 90. So I'm gonna start with the Hamming encoder. Like I said, yeah, we're gonna generate 12 Hamming card from a bit data by adding 4 parity bits. 4 parity check bit. This enables single bit error detection and correlation with the data transmission or storage. Based on the formula and the rule that I already said to you. Based on this table. So um, so what I do in here that P1 which will be is between D0, D1, D3, D4, and D6. With P3 it will be is between D1, D2, D3, and D7. And with the next P2, it will be is between D0, D2, D3, D5, and D6. And with P4 it will be is between D 4, D5, D6, and D7. So this is the architecture of the Hamming encoder or Hamming generator after packaging. So you can see the waveform in here that with the on the bit equal 1, that the 0 to D8. So now the P1 will be equal 1 is all 1 is all 1 is all 1 is all 1, and the P1 will be 1. And the B2 in here will be 1 is all 1 is all 1 is all 1 is all 1, and B2 will be 1 2. And with B3, it will be 1 is all 1 is all 1 is all 1, and it will be 0. And P4 it will be 1 is a 1 is a 1 is a 1, and will be 0 2. And with the next is we have the D0 now is 0. So the B1 now will be 0 is R1 is R1 is R1 is R1, and the B1 will be 0, and B2 will be 0 is R1 is R1 is R1 is R1, and it will be 0 2, and B3 will be 1 is R1 is R1 is R1, and it will be 0, and B4 we do the same, and it will be 0 2. So this is the delay of P0. It will be equal 138 picosecond. And with the P1, delay of P1 is will be equal 113 picosecond. And delay with the P3 is will be 67.99 picosecond. And with the B4, it will be 80. It will be 84.5 picosecond. And we also have the static. And we also have the power of this encoder is static power. It will be equal 355 nanowatt, and with the dynamic power it will be 4.6 microwatt. And the next is the unreliable transmission in cadence. Uh, where after generator, we're gonna send this bit to the unreliable transmission that the bit have ability to change from 0 to 1 or 1 to 0. So to model this performance, we use a noise block that in here. It's very simple that we decided to XOR the original data with the VEDD or VSS because with the VSS equals 0, so 1 is all with 0 will be 1, and 0 is all with 0 will be 0. So you see that the bit doesn't change anything. But when we XOR with the VDD, this means 1. So in this time, 1 XOR with 1 will be 0, and 1 XOR with 0 will be 1. So the bit now is flipped from 0 to 1 and 1 to 0. And here is the packaging of this. And this is a waveform I just assembled. Uh, so you can see in here with the 90 is a VDD, so it's equal 1. So it's always 1, the bit will be flipped. With T0 in here is E1, but after transmission, it will be 0. And the next is D0 will be 0, but after transmission, it will be 1. And with the 9 ones in here, you can see that it's a VSS, so it's 0 now. So the bit D1 doesn't change anything, it's like the same.
Next, I will present the detailed design and operation of the Hamming decoder at the receiver side, which consists of two main blocks. The first is the Hamming checker unit for error detection, and the second is the error correction unit for single bit error identification and correction. The input of the Hamming decoder is a 12-bit Hamming 12A frame received from the transmission channel. This frame consists of 8 data bits from D0 to D7 and 4 parity bits from B1 to B4, arranged in standard Hamming position 1 to 12. And the objective is detecting if there is a single bit error within the 12-bit range and correct if the error lies within the data bits. And here is the bit mapping is as follow. Um, the Hamming checker circuit take the 12-bit Hamming input and produce 4 0 bit output. Um, its purpose is to detect and locate any single bit error during transmission. When the 12-bit Hamming word is received, the circuit will calculate the parity bits using the same equation as the decoder, using the same equation as in the encoder. Detail B1n equal to x3 XOR x5 XOR x7 XOR x9 XOR x11. B2n or B2 nil equal to x3 XOR x6 XOR x7 XOR x10 and XOR x11. B3 nil bit parity number 3 nil equal to x5 XOR x6 XOR x7 and XOR x12. And the last is B2 B4 nil equal to x9 XOR x10 XOR x11 and XOR x12. Then each newly calculated parity bit is compared with the corresponding received parity bit using XOR operation. S1 equal to B1n XOR S1, S2 equal to B2n XOR X2, S3 equal to B3n XOR S4, and the last one, S4 equal to B4n XOR S8. And the syndrome combination S4, S3, S2, S1 indicate the position of the error in the 12-bit sequence. If S equal to 0, no error occurs during transmission, and otherwise, the binary value of the syndrome corresponds to the index of the error bits. And case 1, in the first time interval, on a data bit logic 1, the encoder generates parity bits B1, B2, B3, B4 equal to 1, 1, 0, 0. Since the D0 noise equal to 1, same as the original D0, so the 12-bit RAM is transmitted correctly. The recalculated parity bits at the checker match the original parity bits, so no error detected and data transmission is correct. But in case 2, in this time interval, the transmit data is um, 1, 1, 1, 1, 1, 1, 1, and 0. And the encoder parity bits are B1, B2, B3, B4 equal to 0. However, during transmission, D0 flips to 1 because noise, so the recalculated parity bits differ from the original. So the syndrome is 0, 0, 1, 1. It means that binary tree. This indicates that the error occurs at bit position 3, which corresponds to D0. At other time interval behave similarly, confirming that the Hamming checker correctly identifies single bit errors. And here are the propagation delays of the 4 outputs from S1 to S4. It is slightly different because the number of XOR logic gates is not equal on each pass. But overall, the propagation delay remains small and consistent with CMOS logic behavior. And here is the power variation under different conditions. Dynamic power increases with operating frequency because more frequent switching activity, and static power rises slightly with higher temperature or VDD due to increased CMOS liquid current. Um, Under nominal condition, VDD equal to 1, frequency equal to 50 MHz, and temperature is 27 Celsius degree. The total power is approximately 8.56 microwatt, indicating that a highly energy efficient design. And when VDD increased to 1.2, total power rise significantly. And the second block of timing decoder is the error correction unit. ECU is responsible for detecting and correcting single bit error within the data bit extract from the 12 Hamming code word received from the Hamming encoder. Input signal include 4-bit syndrome S1 to S4 provided by the Hamming checker, and 8-bit data in include data 7 in to data 0 in, which may or may not contain errors. And the output signal of ECU is 8-bit data out from D7 out to D0 out, representing the correct data if an error occurs, or the same data if no error is present. And the error correction unit circuit consists of two main blocks. The first block is The first block is 4 to 16 decoder. This block decodes the 4-bit syndrome into 16 control lines, but in this design, only 8 outputs are used to control error correction for the corresponding 8 data bits. And when S equal to 0, E0 equal to 1, so indicate no error, and on other outputs of 0. But when S different to 0, the binary value of syndrome activate exactly one output y equal to 1, indicating which data bit contain the error. And the second block is XOR correction block, including A XOR A to input XOR gate, A XOR gate. XOR gate has two inputs. The first input is the data bit, and the second input is the correction control signal from the 4 to 16 decoder. If a bit error is detected, means y equal to 1, so dy out equal to dy in XOR 1. So the data bit is inverted, successfully correcting the error. And if no error present, E0 equal to 1, order equal to 0, so dy out equal to dy in XOR 0 equal to dy in. So the data pass through unchanged. And in simulation, the input signal D0 in was correct by fixing it at logic 0. When an error occurs at bit D0, the Hamming check generates syndrome equal to 0011, identify an error at position 3 in the 12-bit Hamming sequence, correspond to bit D0, and the decoder then activate E3 equal to 1, while on other output remains 0. So the corresponding XOR gate execute D0 out equal to D01 XOR E3 equal to 1 XOR 1 equal to 0. So the D0 out signal will restore to its form, proving successful single bit correction. And the remaining bits D1 to D7 were unaffected and passed through unchanged. And here is the propagation delay. The average output delay ranges from 112 to 118 picoseconds, indicating fast response and high stability across data channel. And here is the power consumption. Under nominal condition, the total power is approximately 8.55 microwatt, showing excellent energy efficiency, ideal for low power embedded system. And when increasing VDD to 1.2 volt, the total power rises approximately um, 15.18 microwatt. And here is the symbol of the anti-harming decoder. The input consists of 2 bits. The input consists of 12-bit harming code word, including a data bit and 4 parity bits generated by the harming encoder. And the harming decoder performs two main functions. The first is error detection, carried out by the harming checker, which recalculates the 4 new parity bits from the received 12-bit word. It then compares them with the original parity bits to generate 4-bit syndrome and indicating the position of the error if any. And the second function is error correction. Based on the syndrome value, the circuit automatically flips the error bit if the error occurs in one of the A data bits. Uh, if the error is located in a parity bit, the circuit ignores because parity bits are only used for checking and do not affect the output data. And if no error is detected, the data is output unchanged. And the output of the anti-harming decoder is an 8-bit correct data sequence from D7 out to D0 out, which is fully restored and identical to the original data sent by the encoder. And here is the simulation waveform. When a single bit error occurs at bit D2, which should be a square wave signal up-down, but it is corrupt and held at constant logic 1. After pass through the harming decoder, the two bits is detected and correct back to its original value. On a output bit D7 out to D0 out match perfectly with the original data from the encoder, and single error correction function of the harming code operates correctly and efficiently. Example, suppose the original data and parity generated by the encoder are the data equal to 1111 and the parity bit equal to 1100. If during transmission bit D2 become corrupt, the harming decoder successfully detect and correct the error, outputting the correct 8-bit data sequence, demonstrating that the circuit operates stable and ensure accurate single-bit error correction. And here is the overall system structure, including harming encoder, noise, and harming decoder. The figure illustrates the complete block diagram of the harming code system, which consists of three main modules. The first is harming encoder, accept 8-bit input data and generate 4 parity bits based on the harming algorithm. These are the concatenated into 12-bit RAM for transmission through the channel. The second module is noise block, mean unreliable transmission channel. This block emulates transmission noise. In simulation, the noise block is configured to corrupt one bit within the 8-bit data section of the 12 transmission frame. And the noise block is not a part of the harming code. It only used to validate the system error correction capability. And the last module is harming decoder. Receive 12 bits from the channel and recalculate parity bits, generating a 4-bit syndrome to identify the error location. If no error is found, the data pass through unchanged. But if a single bit error occurs within the A data bit, the circuit automatically corrects that bit. And if the error occurs in parity bit, it is ignored because it does not affect the data output. The final A-bit output matches the original data at the encoder exactly, proving the successful single error correction. And in simulation, the noise logs were configured to flip bit D7. And here is the simulation parameters. And by observation the waveform, we can see that the A output bits D7 to D0 after the Hamming encoder are identical to the original A bit input data. This confirms that the Hamming code successfully detect and correct the single bit errors. And here is the delay measurement at 1 and 1.2 volt. When VDD increased, the average propagation significantly decreased from around 316 picosecond to approximately 290 picosecond. With an average TPD approximately 300 picosecond, the Hamming circuits demonstrate high-speed operation suitable for reliable data transmission systems. Um, and the power consumption analysis. Finally, let's talk about the application and conclusion. Hamming codes are widely used in ECC memory, digital communication like computer network, and data storage. The advantages are that they have a simple structure, easy to implement using XOR gate, and can efficiently detect and correct single bit errors. However, the disadvantages are that they cannot detect double bit error and they increase code length and processing complexity. Um, Overall, Hamming codes are the foundation of many modern error correcting systems, helping to maintain data integrity in digital systems by enabling fast and reliable single bit error detection and correction. Um, uh, and the last is chapter 5, conclusion and future development. Comparison between parity and Hamming code. Both use XOR logic to generate parity bits, but differ in capability. Parity code as a single parity bit can detect single bit errors but cannot correct them. Parity code is more simple and low power circuits. Uh, Instead, Hamming code is just multiple parity bits, can detect and correct single bit error using a single vector. Each circuit is more complex and consume more power and delay, but offer higher reliability, ideal for noisy channel and high-speed memory. Uh, and my conclusion from our study, we successfully design and simulate XOR-based parity circuits and complete Hamming encoder, checker, error corrector. The Hamming circuits detect and correct single bit error with tests under different voltage and temperature in 90 nano CMOS, 90 nanometer CMOS. About the strength, um, our project is simple, accurate, scalable, and low transistor area, but the weakness is higher delay and power. Parity code alone is insufficient for critical system. And the future development and application, we can implement Parity code and Hamming code in ECC like SEC or DEC. That means single error correction and double error detection. or optimize circuits for low delay and low power. Um, and we can apply in ECC memory, wireless transmission, SoC interface, or FPGA and ASIC design. Um, and that's the end of our presentation. Thank you for your listening.